Hello everyone, welcome to Oxford. It's so great to see so many of you here today. My name is Konstantina Vogiatzaki. I'm an associate professor at the Department of Engineering Science, and I'm also a tutorial fellow at Somerville College. Today we're going to talk about a subject that I find very exciting. It's about essentially very cold liquids, and I hope until the end of the talk you also find it, let's say, semi-exciting at least. I know the talk was advertised as a combustion talk, so you might expect very high temperatures. And what I will present today is actually to the other spectrum of temperatures, very, very cold fluids. And I will try to demonstrate how these two things link and how they also link with the big challenges we have to face in the net zero transition. Okay, so I think we're ready to crack on to the material. And I will start the same way as we usually do in the lecture. So when there is a new concept, we start by the definition. So what do we mean by very cold fluids? The other term for that is cryogenic fluids. We essentially refer to liquids. Is everyone okay? Yep. Okay. So cryogenic liquids are essentially very, very cold liquids that before they became liquids, they used to be actual gases. So, for example, nitrogen, or oxygen or hydrogen, in atmospheric conditions they're gases, but in order to store them or transport them or use them, we can impose very high temperatures and pressure, very low temperatures and very high pressures, and convert them to these very cold liquids. And in order to understand that process, you can even use some of the things that you have been taught in your A levels. So when you have a gas and you look at the molecular level, you will see its molecules moving very quickly, being quite far apart here. So when you're a gas, and then when you start extracting heat from these gases, then essentially what you do is you slow down the molecules, you bring them closer together, and you start creating a liquid or a solid. There are two types of cryogens. The one is that the more, let's say, normal ones, like liquid nitrogen, liquid oxygen, liquid methane. And then there is another, a little bit more strange category, which includes at its limits liquid hydrogen. And the reason is because in order to create liquid hydrogen, you need extremely low temperatures, around 20 Kelvin. And then there is something even more strange, helium, which is maintained as liquid in almost close to 0 Kelvin. So this means that you are also start facing some quantum effects. Why do I mention all this? Because essentially, through investigating and giving you a glimpse of what we're doing with the cryogenic fluids, it allows me to explain how some of the subjects we look at here, they have a multidisciplinary character. So already I mentioned something about gases and liquids, which is basic thermodynamics. I mentioned the very low temperatures, which brings quantum effect, and you will see other aspects of engineering, how they come into picture. So where have you seen this fancy, very cold liquids? You might have seen them on TV. It's very popular nowadays with all these famous chefs using them to create these effects with the food. But it's nothing more than a cryogenic liquid that you spray on the food, and because the temperature of the environment is high, then it converts back to gas and create these effects. They are also very popular for food freezing. So any of the foods you have in your freezer, the way they keep them, they help them to be maintained, is essentially they spray it with liquid nitrogen, and you get these frozen foods. So yes, we agree they're kind of fancy, or they can be fancy, but why they are interesting from engineering point of view. Let's start with the finance of the whole thing. Currently, cryogenic market represents a really huge market with potential to increase. So currently, it represents around 17 billion, and the progression is that it will go up to 27 billion. And where is this? What is this market? This market essentially, as humble as it sounds, consists of companies and manufacturers of components relating to these fluids, from pumps to tanks to any chemical industries that they are using these fluids, etc. So if you are an engineer, then you will have to design the systems to optimize them and to control them. So what you need to do so, you need to have an understanding about these fluids. So why are they so interesting? They are interesting because of the range of the application that we find them. So for the sake of this talk, I mentioned like the food industry, but for the sake of this talk, where we're going to focus is in the energy and transportation sector. So you might have all heard about these very strict timelines that we had to reach to a climate neutral condition in the future, and the deadline is the 2050. I know it sounds like far in the future, but for engineering timescales, considering that, for example, a new engine to be designed, developed, prototyped, and put into production, you need at least 10 years. So essentially, the time is very, very pressing. So when you look at the sectors that are the more polluting, this is a picture taken from a report of the Department of Energy and Security and Net Zero. It was published in March in 2024, so very, very recently, and it includes data essentially from the 2023. So the most polluting sectors are transportation and energy. And the problem with these sectors, you might have heard a lot of ideas about electrification, which is a great route to go down. But aviation and marine and some industries are extremely hard to decarbonize using electrification. So we have to find very quickly alternative routes. One of course, the holy grail, actually, it will be nuclear fusion. So if we manage to succeed that, we're fine. We're energy secured. But it's very far away from being a reality. And even this is in this kind of breakthrough technology, cryogenics play an important role. This is from a recent article. As you will see, it says that in order to realize the fusion dream will require cryogenic innovation. They use essentially cryogenics to maintain some of the magnets cool. Okay, but even if we don't look so far ahead and we look our current, let's say, devices that we get our energy from, you might know that cars use IC engines. They are expected also to use fuel cells. For marine, look at here, you use huge IC engines. You have gas turbines to produce energy. All these technologies, although there are still things that we can do and optimize in terms of components, they are mature technologies, even the fuel cells, even the batteries. So the limits of how you can design them better is limited. Even from year one, in your P4 material, which is essentially the energy part, you are going to be taught how each one of these components is operating, the cycles, etc. So hopefully even from year one, you will know how all these devices operate. So system-wise, we cannot really do much. Where we can do things and really bring a change is what we put into our system. And there is where very cold temperatures are important. We will need to use alternative fuels than the conventional gasoline and diesel that are extremely polluting. So we're trying to find alternatives like hydrogen, LNG, other carriers. So if you see the projections, you will see that for the marine sector, for example, the most popular fuels of the future is LPG, LNG, biofuels, and hydrogen and ammonia. These, wherever you see the letter L, essentially means liquefied product and means essentially very low temperatures. So it means that you need to develop technologies that you can that they could withstand these low temperatures, tanks, pipes, even simple things, valves, heat exchangers. All of this technology has somehow to be reinvented to match this very low temperature. Another area that attracts a lot of interest recently, I don't know if you have heard the announcements from Airbus, that essentially they are planning very soon to introduce their zero aircraft concept. Is essentially three concepts. The one envisioned to operate with fuel cells, another with a combustion engine based on hydrogen, and the third one, they plan to do something hybrid. In all of these cases, you will need somehow to bring hydrogen on board. Currently, they're using kerosene. It has a really good energy density that hydrogen doesn't have. So if you start putting hydrogen in an aeroplane, you might need much bigger storage spaces. It's also, you need to tackle safety issues, etc. So it's a whole new technology that you need to reinvent. Even in space, cryogenic fluids have a large applicability. So many of the new spacecrafts, they are considered to operate either with liquid methane nowadays, that SpaceX is looking this approach, or until now it was liquid hydrogen and liquid oxygen. But even if we don't look them from the point of view of our system input, they are also the backbone of many other energy-related technologies. There is currently a company called Highview. It's a UK company that has advertised their products as the biggest cryo battery. It's not really a battery, it's essentially liquid air storage. So you can use cryogenic fluids to store energy, or there has been discussions, especially in US, how you can use cryogenic technology to remove carbon from the atmosphere, so carbon capture. So they're interesting because they have so many applications and they're behind many of the pathways of decarbonizing our future. However, at the same time, they're extremely challenging fluids. In the first 2 years of your course, you're going to focus mostly on what we call like normal fluids, like water, air, some of the standard fuels like diesel or gasoline. You probably will not see this kind of fluids. However, the way we approach these fluids is very similar. So, the first thing we do in order to understand them, we look at the thermodynamic properties. The thermodynamic properties, it's something you will spend almost all your first year here within the P4 material. It is essentially what you know as pressure, temperature, internal energy, properties like this that they characterize what we call the state of the system. So they tell you why something is gas, is liquid, etc. So it's a very fundamental concept in thermodynamics. If we look, for example, cryogenic fluids, what you will see is that they have what we call very, very low boiling point. Boiling point means the point that the fluid changes phases. Again, parenthesis, phase change is one of the subjects you do in year 1 P4. This very low boiling point means that they are extremely cold, not only as liquids, but even when they start becoming vapor. So even their vapor is extremely cold, which you can take advantage in, for example, cooling of modern electronics. And this is now a method that they are investigating for cooling down big data centers. The second property that they have, and it's very important, is that when they change phase from liquid to gas, they expand in volume. And based on the very simple schematic I showed you at the beginning, you can understand why. Because they start absorbing heat from the environment, the molecules start moving quicker, going apart, and they expand and they start occupying much more volume. This can be a good thing because it has been suggested that, for example, it can replace the combustion process. So what is really happening when you have combustion? You burn things, the gases expand, and they move the cylinders. In theory, it can work the same way by injecting a cryogen, that by absorbing the heat, it expands and moves the cylinder. Of course, it sounds very promising, but as everything that it sounds good has its own practical problems, and nowadays the problem is how much energy you spend in order to create these liquids and then use them to produce energy. So the energy balance doesn't really make sense currently with the current technologies. And another side of this expansion, which is currently very relevant and has created a very negative, for example, perception of the public about the wider use of hydrogen, is the safety issues. So if you start putting them under very cold temperatures and at the same time high pressures and try to maintain them in a tank, what it will happen, these fluids have the tendency to return back to the gaseous states and expand. So if something is not controlled or predicted accurately, you might have this thing happening here. These leaks, which is a big problem for safety. So in order to understand how the different devices that we try to design, and designing is a large part of engineering, is based on these diagrams that we call phase change diagrams, which essentially show you how, knowing the pressure and the temperature of a fluid, you can predict the state that the fluid will be. So you can predict what will happen if you start changing pressure and temperatures. The diagrams that I showed you are mostly representative for normal fluid, as I said, for water, for air, for any of the fluids that you have seen in your A levels. Cryogenic fluids have an extra property, which is that they very quickly become supercritical fluids. I don't know if you have heard about this term ever. Anyway, these are the problem is that the applicability map of these fluids into the application leads the fluids to become supercritical. Practically, supercritical means what you see in the figure here. It's a liquid that surprisingly is neither gas nor liquid. It's somewhere in between. It has properties between the two states. And this is really a very new field with many applications. It's used in energy. It's on its own a field of study. You will touch upon that a bit later in your studies, but not, of course, immediately. So, with all these very strange properties, how can we understand more about these fluids? In order to use them, we need to understand them. So I gave you the kind of the theoretical background. This, you can understand it even only with the material of first and second year. But if you try to design something new, the next step you have to take is do experiments. You go to the lab and you have to do some experiments. And again, here you will have the opportunity the first 2 years to do roughly 5 hours per week of lab work, so to understand better how devices are working, which parameters you can play with to optimize them, etc. The problem when we're talking about cryogenic fluids is that experiments are very expensive because of the safety considerations. For example, it's very hard to bring in a facility these gases. You have to pass all the risk assessments, etc. And some of them, they are flammable, so it means that if they leak, they might cause unwanted effects of fires, detonations, etc. So let me show what I mean. This is a picture from a NASA storage tank. You see the sizes of these tanks, that they transfer essentially liquid hydrogen to these tanks, and then they will move it to the spacecrafts. So what might happen is, if the valves, they use valves in order to release the pressure. If any of the valves don't operate properly, you have a release of hydrogen, which is a flammable material, and then you might have something like this up there. I don't know if you can read it. It says that this kind of fireballs travels with 170 meters per second. They're extremely quick events. Also, you can see the scale of these events. So if you want to represent them in a lab, it's extremely hard to control this and understand what is really happening behind this. So what I'm working on is an alternative route that, again, you might have heard the term, is called digital twinning. So instead of putting yourself in all this trouble of going to the lab, trying to bring the cryogens into the lab, having to pass all these safety considerations, you can create computer programs that can allow you to investigate physical phenomena in a more controlled and easily accessible manner. Of course, all this means that you know the fundamentals, you have formed the proper equations. So you need thermodynamics, you need fluid mechanics, you need material science, etc. At the same time, in the work we're doing, it involves many aspects of computer science, because then you have to take these equations and put them in a computer, program them, essentially. What you see here, for example, is with a program called OpenFOAM. It's an in-house code we have developed, no, not OpenFOAM. Some libraries in OpenFOAM are in-house, and it works on C++. And what you can see here is, let me see if it's running. Yes. We have reproduced a liquid nitrogen jet. So it's just a simulation of a physical behavior. On its own, yes, it's cool, but it doesn't tell you anything. So how do we use this? One of the things that we can do, for example, is we can start understanding what happens inside this jet. So you can cut slices, you can look inside, etc., things that you cannot do easily in a real experiment. So you can get optical access in areas that you don't normally have. Another thing you can do is collect data from your CFD and use them as training data for predicting things through machine learning approaches. For example, if you take that jet and you probe it in one point, you can measure the pressure. And you will see a pressure signal like this. You can use this data to train your algorithm and then predict the rest of the behavior of the phenomenon. So that's another use of them. A third one is looking at scales that normally, even if you can do experiments, you cannot really look at. What you see here is just one liquid oxygen droplet that inside contains these sides of vapor, that if you change the outside pressure, what will happen is these points will start expanding and burst this droplet. This is not something you can really reproduce easily in an experiment, and the only way you have to do is these tools. So that is only a part of the research that I'm doing. We use this, for example, we provide these codes to fourth-year students or master students, also some intern students, depending on their interest, so they can play a bit around and try different things and participate in actual projects. All of these that I showed you are funded either from industries or from the UKRI, which is the Research Council, so they're part of real projects. Well, of course, we don't expect you to immediately day one start developing these tools, but at least you get a feeling of the things that you can do if you follow this pathway, which is only a very small path among all the other things that you can do in a general engineering science department like ours. So with this, just to thank you for your attention. And if you have any questions, I'm very happy to answer them.